Uh, okay. So welcome back, everyone, to this week's QTFMS seminar. Today, we're delighted to have Anatoly Dymarsky from the University of Kentucky. He'll be talking about his work regarding the relations between Eigenstate Thermalization Hypothesis and conformal field theories. Anatoly, you can start whenever you're ready.
Okay, thank you so much for an invitation to give an online seminar. I would like to speak about our recent work, which actually several works. They both works appeared last September, and in those works we use the diagonal approximation. I will explain what it is. It's a particular approximation which is inspired by semi-classical physics to calculate entropy in two-dimensional conformal field theories. So let me start with the plan of my talk. I will go slowly and first explain the idea of semi-classical diagonal approximation. You will see clearly why I call it the diagonal approximation. Then I will apply it to calculate subsystem entropy in two-dimensional CFTs and high-dimensional CFTs. And then we will revisit two-dimensional CFTs. And I will explain that in two dimensions, any conformal field theory has an integrable sector. It has infinite number of conserved quantities, conserved charges. And if you try to do Eigenstate Thermalization Hypothesis carefully for two-dimensional field theories, you have to include those conserved quantities into account. And once you take them into account and apply ETH, Eigenstate Thermalization Hypothesis, you can calculate the subsystem entropy, and we will calculate it time permitting for different ensembles today, including the ensembles which are charged with respect to this additional conserved quantities. And we will resolve some of the old puzzles between some of the old puzzles tensions between which precluded some puzzles related to the way how Eigenstate Thermalization Hypothesis is formulated in two-dimensional CFTs. I'll explain a little bit better once we got to the slide. Okay, so this is the plan. I assume the talk is informal in the sense that you will be interrupting me with questions. I'm very open to that. So if you see that something is not clear, please stop and ask questions. Okay, very good. Next slide. This slide is completely taken from the textbook. It's basically follows any statistical thermodynamics or statistical mechanics textbook. Let me remind you how that usually goes. You don't have to look at the formulas on the slide. You just need to remind yourself the first chapter of pretty much any textbook about statistical thermodynamics. You try to understand what the microcanonical ensemble is. And in classical setting, there is no notion of microstates. So if you have classical system, you do not know what microstates are. So even if you're a classical physicist, but you try to do statistical mechanics, you have to introduce something like a quantum state. We call it microstates in statistical mechanics. What they are states of the quantum mechanical Hamiltonian. And then you say that you have a big system and you split it into two parts. The subsystem, which you will call A, and the complement, which we will call A bar or complement of A. And then the axiom of statistical mechanics is that if your isolated system has total energy E, then you have equal probability to find that whole system in any microstate with that energy. Okay? How do we formulate that quantum mechanically? Quantum mechanically, we say that you have a system, a full system. You split it into subsystem A and its complement, and the volume of the system is the sum of volumes. We assume that the system is large, the subsystem is sufficiently large, the area which separates the subsystem and its complement is small in terms of the volume. It's the area. To get the volume of the area, you need to take the area and multiply by atomic distance or some other cutoff which you introduce. So the volume associated with the area between the subsystems is negligibly small. Therefore, all the boundary terms, all the sub-extensive quantities are unimportant. You assume that your energy is extensive. You assume that your entropy is extensive. And then we make the next assumption that the total energy of the system is E. What is the microcanonical ensemble? The microcanonical ensemble is the probabilistic ensemble of energy eigenstates with energy equal to E. Usually you have Hamiltonian which is not degenerate. So if you specify E precisely, there is only one microstate. There's only one quantum state with exactly the same energy E. So you consider a certain window around the mean energy, and you take with equal coefficients all the eigenstates which fall into that window. So this is the microcanonical ensemble. Okay, this is what classical statistical mechanics means when it says that in the microcanonical ensemble you have equal probability to find your full system in any microstate. Okay, so this is not the end of the story, because usually the textbook, and the textbook I particularly like is the one by Charles Kittel, that's the picture here. It proceeds to discuss a probability to find a subsystem in a particular microstate. For that, you need to split your Hamiltonian into the Hamiltonian of a subsystem and the Hamiltonian of the complement. And to be able to do that, you need to be able to neglect the boundary term. We assume that you can do all of that. For that, you need the Hamiltonian to be extensive. That's what I meant here. Energy is extensive. Then you ask, what is the probability to find your subsystem in any particular microstate? Well, if your full system can be found in any microstate associated with a full energy E, then your probability to find your subsystem in a particular energy eigenstate is actually proportional to the number of microstates associated with the complement. So capital E is the energy of the full system, curly E is the energy of the subsystem, capital E minus curly E is the energy of the complement. And by omega, I denote the total density of states. And so omega with the subindex A bar is the density of states of the complement. So this is the total number of microstates of the complement with the energy capital E minus curly E. So this is the standard calculation of statistical mechanics. The probability to find your subsystem in a particular microstate is proportional to the number of microstates of the complement which are available to you given the energy balance. Okay, so basically what I'm writing here in this formula is nothing new. It's not something we introduced. This is just rewriting in a quantum mechanical language what a statistical mechanical what a classical statistical mechanics would tell you. But again, classical statistical mechanics is secretly always quantum mechanical because they talk about microstates, and microstates are the eigenstates either of the full Hamiltonian or the subsystems. So you get this nice formula, very simple formula, which tells you that the reduced density matrix of the microcanonical ensemble, you take the microcanonical ensemble of the full system, you reduce it to the subsystem, and you calculate the matrix element of this reduced density matrix in the eigenstate of a subsystem, and it's given by the ratio of the total density, it's given by the ratio of the total density of states of the complement divided by the total density of states of the full system. How do we know that this formula makes approximate sense? You can try to calculate the trace of the reduced density matrix by summing over all energies of the subsystem, and you should get identity because the reduced density matrix should be normalized such that the trace is 1. And indeed, if you try to do this calculation, you will get the identity, at least approximately within this saddle point approximation. You will have to multiply this right-hand side or left-hand side by the density of states of the subsystem and integrate over all possible energies of the subsystem. You can do this integral with a saddle point approximation, and approximately density of the full system is the density of a subsystem multiplied by the density of states of the complement. And because of this formula, you will get identity on both sides. So that's like a consistency check that this semi-classical formula is correct. Okay, so again, I wouldn't say that there is anything new. That is just rewriting the classical textbook of statistical mechanics. Let's try to move forward, and let's try to consider a quantum system which is chaotic. What is chaotic is difficult to define, but let's assume that the system doesn't have any obvious symmetries. And then people proposed that such systems, they would satisfy additional very intricate and interesting property called eigenstate thermalization. The formulation of that statement usually goes under the name of Eigenstate Thermalization Hypothesis. The Eigenstate Thermalization Hypothesis claims that individual energy eigenstate is thermal if probed by, let's say, a local local observable. Usually, in the context of Eigenstate Thermalization Hypothesis, people write down this, people write down this ansatz for the matrix elements, and that's fine. We can think about ETH in these terms, but more physically, what ETH tells you is that if you have a system prepared in a coherent state in the individual energy eigenstate, something which is not observed in nature, which might be observed on a quantum computer or in the lab, but this is difficult to prepare because you want to prepare your system in a coherent state. According to theorems of quantum mechanics, you might need an infinite amount of time to tune your system to an individual energy eigenstate. Then, if you probe your system locally, you will not be able to distinguish it from thermal system. So this is the context of eigenstate. This is the content of eigenstate thermalization hypothesis. In conformal field theories, you can reformulate this statement as the statement about operator product expansion coefficients, the OPE coefficients. We did that in 2016. But then in two-dimensional CFTs, there are actually two versions of this statement. One version is related to the statistics of OPE coefficients. There is some statistics of matrix elements hidden here, and inspired by that, people talk about statistics of OPE coefficients. But there is a subtlety here, that there is another aspect of ETH in two dimensions, is that you can, even if you talk about thermality of eigenstates, not everything is rooted in, not everything is related to OPE coefficients. There is also a need to take care of the integrable structure. And I will explain what that means and how to do that next in the talk. But before we proceed with two-dimensional CFTs, let me give you an intuition.
Can I ask a question?
Yes, of course.
So if you take the two-dimensional CFT to be a rational theory, what is the corresponding thing in the ETH side?
Well, if you have a CFT to be rational theory, then the whole theory is integrable. So presumably ETH by itself is not satisfied. There might be a different statement, similar to the statement which will appear in my talk later, but a different one where you introduce all the conserved quantities, and then you don't say that individual energy eigenstate is thermal, but you say that individual energy eigenstate. What is thermal? Thermal means that you locally cannot distinguish it from the canonical ensemble. But if you have other conserved quantities, then your ensemble will know about those quantities. Okay, and therefore you will talk about generalized Gibbs ensemble. Canonical ensemble or thermal ensemble is also called Gibbs ensemble. If you have many quantities, then you should be talking about generalized Gibbs ensemble. So for rational CFT, it might be possible to say, I don't think it was done, but it might be possible. I once worked with my former student on this, but we did not get to any tangible point, that individual energy eigenstate is indistinguishable from a particular generalized Gibbs ensemble. Okay.
Thanks.
So let's see how ETH works in conventional systems, something like spin chains, where you have no additional symmetries. Well, if you have no additional symmetries and you try to calculate an expectation value of some local operator A in eigenstates, this is the plot on the right-hand side. On the horizontal axis, you have energy density. On the vertical axis, that's the expectation value of a local operator in the energy eigenstate. You see that these expectation values form a very nice smooth curve. Basically, that's universality, because if you consider a particular energy eigenstate or you consider a microcanonical ensemble, the result will be the same. If you look at the integrable system, that will be a qualitatively different story, because there is no nice smooth curve. You have a whole cloud of points. So you should understand that on the horizontal axis, I have energies of individual eigenstates of the Hamiltonian. In this case, the Hamiltonian has 17 spins. So it means that I have roughly 130,000 states. So I have 130,000 points on the horizontal, on the horizontal axis. And therefore, they're very, very, very dense. But it's very clear that if I consider two consecutive points on the left plot, the corresponding value of the matrix element could differ a lot. If I consider two consecutive points on the right plot, corresponding expectation values will be very, very close. So there is certain universality in the case of a chaotic system. There is no universality in case of integrable system. Okay, that's how conventional ETH works. Any questions about conventional ETH? So now let's try to say that I have a system satisfying ETH, and I want to combine that with the logic I had in the beginning of my talk, where I had a system split into subsystem and its complement. Now I consider a system in the individual energy eigenstate. I'm not considering microcanonical density matrix. I'm considering a reduction of the individual energy eigenstate. This is a reduced density matrix which comes from the individual energy eigenstate. Well, this is the full matrix. This is a reduced matrix. The statement of ETH can be formulated as follows. If you consider two consecutive energies or two eigenstates with very, very similar energies, E and E prime, corresponding density matrices should be very, very similar to each other. You do not have to demand that those density matrices are thermal or similar to be thermal. You don't have to demand that. That will come out automatically. The only thing you demand, and this is the formulation of subsystem ETH, how we formulated it in 2016, is that if you consider two energy eigenstates with similar energies, corresponding density matrices are very similar to each other with respect to trace distance or any other quantum measure, and the proximity should be exponential. That is the formulation of subsystem ETH. It is illustrated here if you consider two similar points if you consider two energies with approximately equal values, corresponding expectation values will be exponentially close to each other. If 2 points are exponentially close on the x-axis, they will be exponentially close on the y-axis. That's the idea. So once you declare that you have universality, you'll automatically obtain that the reduced density matrix of individual energy eigenstate is approximately the same as the reduced density matrix of the microcanonical ensemble. And then remembering that we calculated matrix elements of the reduced microcanonical ensemble, you can immediately recognize, and this is a result of our, I have this problem with my presentation switching between slides. I was trying to tell you about the result of our 2016 paper, that if you have an individual energy eigenstate and you combine that with the logic from the beginning of my talk, you immediately recognize that diagonal matrix elements of the reduced density matrix are approximately given by this formula. Okay? So basically, we calculated diagonal matrix elements of a reduced density matrix for any excited eigenstate of the full system. So here omega is again density of states. We can write it in terms of thermodynamic entropy. Omega is equal to e to the s. We have entropy of the full system, and we have entropy of the subsystem. Now, what about off-diagonal matrix elements? Similarly to the conventional ETH ansatz, and this is the conventional ETH ansatz, where you have the exponential suppression of off-diagonal matrix elements, you can argue that the off-diagonal matrix elements of this matrix will be small, and therefore maybe they will not matter for certain things. What are the things for which they will not matter? We claim that they will not matter for subsystem entropy. Now, basically, I'm saying that this formula calculates the reduced density matrix of an individual energy eigenstate. You can completely forget about off-diagonal matrix elements and simply use this diagonal matrix. This is like a diagonal matrix to calculate the subsystem entropy. This approximation, we will call it semi-classical diagonal approximation. Semi-classical because it basically comes from the classical statistical mechanics. You can forget about the word semi-classical because the system doesn't have to be semi-classical. You can call it a diagonal approximation because we assume that matrix rho A is diagonal. So basically, this is the idea that we calculated the form of the subsystem density matrix, and we will use it to calculate the subsystem entropy. Any questions about this? I know I was going very slowly with this and spent a third of my time, but I think it was worth it because that is the idea of what we are doing. Everything else is technicalities, maybe technically complicated things, but conceptually nothing on top of this. Yeah.
I do have a question. Does subsystem ETH have any relation with spin correlation function?
Spin correlation function?
Yes.
I do not know what that is.
Okay.
Maybe you can tell me a little bit about the spin correlation function.
Perhaps I can ask after we can talk after the presentation.
You mean a correlation function of spin operators?
Yes, yeah, exactly.
Well, Eigenstate thermalization is a statement about eigenstates, and the statement is that if you calculate correlations in that eigenstate of any operators which are sufficiently local, the result will be the same as in the thermal ensemble. So if you calculate expectation values of one spin operator, two spin operators, or a few spin operators in an energy eigenstate, the result will be exactly the same as if you would calculate it in a thermal ensemble.
Yeah, okay, thank you.
Okay.
I also have sorry.
Oh, go ahead.
So I was going to ask, like, can we reproduce these results from an algebraic perspective? Like, if we consider the von Neumann algebra acting on the subsystem A and its commutant, which acts on the A bar system, can we reproduce these results?
I do not think so. I think you want to get this result from some formalism, which is universal and describes both integrable and chaotic dynamics. This is not a result of any symmetry. In fact, this result is a result of absence of symmetry. This is a universality which emerges from chaotic behavior, right? So you should ask yourself a question: how would you see universality coming from chaoticity in your formalism of von Neumann algebra or any other formalism? I think that's very, very complicated, and basically not something people can do rigorously, right? So I don't think von Neumann algebras would have any help here. I could be wrong, of course.
Okay.
There's some work on this in the context of modular operators. So you look at the spectra of the modular operator in a given von Neumann algebra. And this tells you something about holography. The details are maybe unimportant, but people have thought about chaos in that setting.
There might be two different things here. There might be important subtleties related to the fact that we want to apply that to CFTs, and in the CFTs, you cannot separate a system and a subsystem and its complement. The Hilbert space is not factorizing, and therefore you need to talk about von Neumann algebras and all of this sophisticated mathematics. That is certainly important in CFTs, and I'm sweeping that under the rug in my talk. In my talk, I did not make any distinction between CFTs and spin chains. I simply assume, I will have a comment on one of the slides, that I assume that all those technical things can be solved somehow. But you can think about spin chains where everything is factorizable, Hilbert space is factorizable. Von Neumann algebras are of type 2, if I remember correctly. They're simple ones, they're finite ones. There's no problem at all. And interest in physics is present there. You can consider modular Hamiltonians. You can calculate the spectrum. It's known that has been done in the chaotic systems. The modular spectrum of the modular Hamiltonian shows level repulsion, that the sign of chaoticity. But showing that explicitly, analytically, is very, very complicated. Even though there is no issue with the von Neumann algebras and no need to worry about the splitting of the Hilbert spaces. Just the idea that you want to treat chaoticity and analyticity and try to see how this universal behavior emerges microscopically, that's already a very, very difficult problem. Okay, and then you have this issue with the non-splitting of the non-factorizing of the Hilbert space on top of that. But I don't think it's crucial here. I think when it comes to chaos, at least I do not know any work or any evidence that non-factorization of Hilbert space in field theories is important in the context of chaos. Okay?
Yeah, thanks.
I have a different question as well. So when we're neglecting the off-diagonal entries, like somehow in the regular ETH, that tells you also about fluctuations about the thermal equilibrium, which are somehow exponentially small.
That tells you everything. It tells you everything. It tells you the dynamics. Without off-diagonal matrix elements, you have no time dynamics.
Exactly. So in this case, when you have this semi-classical approximation, do you lose all the dynamics?
Yeah. We are agnostic about the dynamics, and the claim I have is that with this approximation, we can faithfully calculate the extensive part of the subsystem entropy. So you have a large subsystem. The system is huge. The subsystem is large. You can calculate the extensive part of the subsystem entropy. I'm not even sure how to calculate corrections in a systematic way. I'm not talking about fluctuations because of the dynamics. I'm talking about sub-leading, sub-extensive corrections related to the boundary terms. You see what I did here? Not only I forgot about non-factorization of the Hilbert space, I basically said, think about a CFT, simple CFT, which emerges from the spin chain tuned to a critical point. Okay, you have a spin chain tuned such that there is no mass gap. So when you consider many spins, 1,000 spins, 1,000,000 spins, you will essentially have long wave dynamics, which is a CFT. Okay, this is a rigorous result. You can obtain CFT this way. Now, there's no issue with factorization here because you're secretly working on a lattice. If you split your system into subsystem and the complement, there's always an issue of the boundary Hamiltonian. What kind of boundary conditions you impose? Here, I'm agnostic about that because I'm calculating extensive quantities. So far, my quantity is extensive, energy or entropy, they're extensive. My claim is it doesn't matter what kind of boundary conditions you introduce. If you're working in a CFT, you probably want to introduce boundary conditions which preserve conformality. There might be several choices. There might be unique choice. I'm completely agnostic to that. If you want to calculate corrections which are sub-extensive, order 1 corrections, you have to go back and ask yourself a question, what kind of boundary conditions you impose. And then the fact whether you're working on a spin chain or in a continuous CFT, all of these things might be important again.
Okay, yeah, but for the extensive part, the semi-classical just captures that extensive piece.
Yes.
Is the claim.
That's the claim.
Sense.
That is the claim. That is based on the physical. I'm not trying to prove anything, but it's based on the physical intuition, semi-classical intuition, if you wish.
Okay, thank you. Yeah, makes sense.
Yep.
Can I also ask a small question? So we must have, in subsystem ETH must give a regular ETH, right?
Oh, yes. It's a stronger statement, yes.
Okay, thank you.
Yeah. It's included. The conventional ETH statement is included here. That's a stronger statement. It's a statement that you can reformulate it like that. From this statement, you can get that conventional ETH is satisfied for any operator confined to a small subsystem. And the opposite is true. If the conventional ETH is satisfied for any operator confined to a small subsystem, then the subsystem ETH also works for that small subsystem.
Okay,
the subsystem doesn't have to be particularly small. We argued in our 2016 paper that it can be as big up to 1/2 of the full system. So it could be a third, it could be 45%, 49%. Okay. All right, so now let's use this new insight. Let's try to calculate subsystem entropy for some interesting physical system. How do we do that? Well, before we do that, I forgot I have another slide, but it's a simple slide. We basically say, okay, let's use this diagonal approximation to calculate entropy. So you have the full system, you split it in a subsystem and a complement. F will be the fraction. That's the fraction of the subsystem with respect to the full system. So we will take F to be smaller than 1/2. Also, in certain cases, you can keep it up to 1, which means that the subsystem could be as big as the full thing. And then it depends on your original ensemble. If your original ensemble is the energy eigenstate, then all I'm going to say will require F to be smaller than 1/2. But if the original ensemble is the microcanonical ensemble, then according to statistical mechanics textbook, my subsystem could be as big as you want. It could be almost the same as the full system. So F is the fraction. Then I consider my original system either in the microcanonical ensemble or in the canonical ensemble. What's the difference? The microcanonical ensemble is when I fix the energy of the full system within a certain window, and I say that all microstates are equally probable. Canonical ensemble is a different ensemble where I weight my microstates with a probabilistic weight E minus beta energy. They're similar, but they're different. There is a theorem that these ensembles are equivalent if you probe the system locally. But in reality, those two ensembles are different ensembles, and they apply to two different physical contexts. Microcanonical ensemble describes an isolated system. Canonical ensemble is describing a system which is connected to a thermal reservoir, to a thermal bath. These are two different physical scenarios. You can calculate reduced density metrics for both cases, but the formulas will be slightly different. This is a reduced density matrix in the diagonal approximation. When the full system is in the microcanonical ensemble, this is the formula when the system is in the canonical ensemble. If your subsystem is sufficiently small, then this energy, Curly energy, is much smaller than the full energy, and you can expand these formulas to the leading order in E, and then this formula will become this formula. Which means, and this is a standard thing in statistical mechanics, that if your subsystem is sufficiently small, you will not be able to distinguish between microcanonical and canonical ensembles. But if your subsystems are large, these are two different ensembles, and the reduced density matrix of those two ensembles are two different matrices. That is important. That is not always appreciated. It's not that this is something new, but this is something which people do not always appreciate. So one of the results which we noticed back in 2016 is that even though those two density matrices are different, if you calculate one Neumann entropy, the extensive part of one Neumann entropy, because that's all we can calculate within this approximation, they will yield exactly the same extensive part of one Neumann entropy. But if you calculate Rényi entropies, then the Rényi entropies will be different. So if you're interested in one Neumann entropy, you're sort of blind with respect to the ensemble or the state of the global state of your system. But if you calculate Rényi entropy, they're much more sensitive, and they will tell you if your system was in a canonical or microcanonical ensemble. Of course, that requires the subsystem to be a finite fraction of the full system. If you consider the subsystem to be of fixed volume, while the rest of the system goes to infinity, this is called thermodynamic limit, then the subsystem is so small, this F fraction goes to 0, you will not be able to distinguish the ensembles. Okay, with this very long introduction, let me now start calculating entropies. I'm trying to see how much time I have left. Let me try to start calculating entropies, and I will start with the CFT. Why with the CFT? Because
before that, sorry,
yes.
Before that, there's a question that I can read for you, or can you see it? Okay.
Can I see the question?
I can also read it. Okay.
For any subsystem A that is less than half of the system, the complement A bar acts like a heat bath. Are you saying anything more than this? I'm not saying anything more than this. I'm saying exactly this, that for any system, subsystem A, the complement works as a heat bath. But the statement that this applies even when the global system, the full system, is in the energy eigenstate, this is a very non-trivial statement. It cannot be deduced from classical intuition, because classical intuition doesn't know what a coherent state is. Okay, so it's nice that even for very quantum, very coherent states, you can apply classical intuition. And in that sense, everything is simple and trivial. But this statement by itself is not a simple statement. The intuition is very clear, but if you want to prove it, you will have very hard time proving it. It hasn't been proved even once, even for any simple, well, there are very simple models where it has been proved, but it has not been proved in any realistic model on a lattice or anything like that. Okay, so now if I want to use these formulas on this slide to finally calculate something, what do I need to know? Well, I need to know entropies, entropy function, thermodynamic entropy, or the density of states of my subsystem and the complement. So you can think of a subsystem as a subsystem A. It doesn't have to be exactly like its complement in terms of the physics. Subsystem A could be a bunch of spins. Its complement could be thermal reservoir with a gas, or I don't know, a pool of water or something like that. So they could have different physical nature, but I will be able to calculate things if I know density of states for these corresponding Hamiltonians. The simplest scenario, when I have a homogeneous system, like a field theory, and I split it into two parts, or I have a room of air, like I have in my room or you have in your rooms, and you split it in your head into two parts. Then you have air in one part and you have air in another part. Everything is homogeneous and translationally invariant. In this case, you need to know these functions, and this function will be very simple function of energy density, volume, and other things, right? These are the functions we discuss in the course of classical thermodynamics. In case of conformal field theory, things will simplify even more because conformal field theory is, first of all, scale invariant. And if you want to write the density of states or entropy function, which depends on full energy and full volume, the form of this function is fixed by the requirement that this function is A, scale invariant, B, extensive. Entropy is extensive. Therefore, you can safely say that in conformal field theory, entropy will be proportional to the volume, and something which is not extensive, which is intrinsic. Intrinsic property of a gas is temperature. That's the only quantity you have here. So you have temperature, which you take to the power such that this whole thing becomes dimensionless. Okay, so basically scale invariance guarantees that entropy is given by this formula, and the only thing which is not fixed is this coefficient kappa. In two-dimensional conformal field theories, this coefficient kappa can be related to central charge. In high-dimensional conformal field theories, this coefficient kappa cannot be related to central charge. It's something less universal. We do not know how to calculate it, but up to this one number, which characterizes the whole theory, we know the entropy right away. And once we know entropy, in full universality, you see for any dimension, I can use this formula. I can take this formula, plug it into these equations, and take this to any power n if I want, and calculate Rayleigh entropy. And that can be easily done. Now, again, going back to the discussion of von Neumann algebras, here I simply assume that I can split my field theory into subparts, and there is a notion of an eigenstate of a subpart. That usually requires a lot of mathematical peculiarity, a lot of mathematical work to show that you can define a Hamiltonian of a subsystem, an eigenstate of a subsystem. But I always will keep in mind that there is some lattice regularization, and I will simply forget about all these technicalities. I will assume that a subsystem has eigenstates and stuff like that. Then you do a saddle point approximation calculation. It's a trivial calculation. You immediately obtain Rayleigh entropy for the canonical ensemble and Rayleigh entropy for the microcanonical ensemble. Well, we did this calculation last September in the paper which appeared last September. Of course, the results have appeared in the literature previously. In the case of canonical, microcanonical ensembles, the calculation was done in the holographic context. And in fact, the holographic calculation is literally the same calculation. Not only the result is the same, but the calculation is the same, because the way people do the calculation in the bulk is secretly also the same diagonal approximation. That hasn't been appreciated much before, but we make this connection much more clear. And in fact, we have another paper which appeared on the same day where we explain that a little bit more. So, of course, these results agree with Calabrese-Cardi explicit results and all other previous works. So there is little doubt that diagonal approximation yielded correct result for the subsystem entropies. Okay, so what I want to say is that we put very little to obtain these explicit formulas. We basically assumed that things will behave like in a semi-classical setting, in a statistical mechanics setting. We use scale invariance to write down explicitly entropy, and that's it. And we used saddle point analysis of an integral. That's it. You don't really have to work hard to get those formulas. That's the beauty of this approximation. That's why this approximation is very powerful. Next, you can try to apply the same logic to primary state of two-dimensional CFT. Primary state is an eigenstate, so you can try to use this formula, but there is some nuance, which is explained in the paper, that prime state is a very special eigenstate, and if you reduce prime state to a subsystem, the expansion in terms of the eigenstates of the subsystem should also include only prime states. I know that might sound a little bit confusing. I want to refer to the paper if you want to know details. But basically, you can use the diagonal approximation to calculate the subsystem entropy of a primary state. That was done in our paper. But in fact, much earlier, it was done by my collaborator, Huaja. Huaja is a co-author of this recent paper. He co-authored a much earlier paper with Tom Faulkner, where they calculated subsystem entropy of primary states using a completely different method, which is called the method of monodromy. Much more complicated CFT-specific method to calculate entropies. This is the result. The result is simple and nice, but it's strange because this is Rayleigh entropy, and Rayleigh entropy has an index n, and there is no n on the right-hand side. It's not a mistake. It's a very peculiar, very unusual behavior, that somehow Rayleigh entropy is index independent. That is confusing. Okay, you can say primary states are very special states, but what about Eigenstate Thermalization Hypothesis? If eigenstates are thermal and primary state is an eigenstate, of course, then we should try to compare this with the microcanonical ensemble. Well, you can try to compare it with the canonical ensemble, although that is not correct. The correct version of ETH is to compare eigenstate with the microcanonical. And sometimes canonical and microcanonical will be the same. That's when this subsystem is small. But in any case, if you compare with canonical or microcanonical, both are dependent on index. This is not index dependent. By the way, I mentioned on the previous, this formula is exactly the same formula for the microcanonical entropy, just in case of two dimensions. And here I'm quoting much earlier work by Shidon, who calculated that holographically. That's what I meant here, that disagrees with the earlier works, including holographic computations. So Shidon calculated this holographically, and there is a discrepancy between this and this. What does it mean? Does it mean that ETH is not satisfied? That was
a question.
Yes.
Oh, sorry, go ahead. Sorry.
No, go ahead.
Oh, I want to ask you, so usually you don't expect ETH to apply to all eigenstates, but rather middle of the spectrum, you want the continuum so you can define an energy, just like in a thermodynamic sense, right?
Yes.
Would you expect in the case of primaries that these are satisfied?
Yes. So you're raising the following issue. You're saying we don't expect ETH to apply to all eigenstates.
Yes.
And indeed, if you have eigenstates very, very close to the boundary of the spectrum, you cannot. Do you see my mouse?
Yes.
Okay. I'm showing that there are states at the edges of the spectrum which do not satisfy ETH. This is true. The expectation is, though, and I think we discussed it in a 2016 paper, that as the size of the system increases, states with any finite energy density, or in other words, states with any finite effective temperature, should eventually start satisfying ETH, meaning that those boundary effects will be confined to smaller and smaller and smaller and smaller energy densities. Not
right,
energies,
totally agree.
but
yes.
Energy densities. Okay, so here we are talking about CFTs, but we are always, I don't have a slide about that. I used to, but it's very technical, so I removed it. We always assume thermodynamic limit. You assume that you have a spin chain will becomes infinitely large. In case of a CFT, it means that your spatial circle becomes infinitely large. Now, CFT people don't like that because CFT people say it's a conformal field theory. I can always rescale spatial circle to be of unit radius. You can do that easily, but it means that we are considering states with infinite energy. So this state's delta we are considering, is very, very large. So actually the formula I need is here. Delta is the energy or dimension of the primary. C is the central charge. Beta is effective temperature. And L is the radius of a circle. Okay, so in my notations, which I like, more physical notations, when you think about spin chain, you should take L to be infinity. If you are more like a CFT person and you want radius to be unit and the circumference to be 2 pi, you say that L is a formal parameter and you take L to be infinity, or in other words, you take delta to be infinity. You take delta to be very, very large. That's the limit where you expect ETH to apply. And then the question is, do we expect ETH to apply to all states? Yes, there are no outliers in the middle here. It's a separate question if there could be, and there is this whole different topic of quantum scars. It's a completely different sort of story, that you have very special sectors of your theory and stuff like that, and you have states which do not satisfy ETH. But normally we do expect that states satisfy ETH, and the issue here is that it's not that one particular primary state will not satisfy ETH. All primary states will not satisfy ETH. All of them, right? So something is odd. You cannot say that ETH is satisfied if primaries do not satisfy ETH. And the conclusion is that, in fact, ETH is not satisfied. That's the right way to think about it. What is satisfied is the generalized version of ETH, and maybe I should try to explain what it is, and that's the rest of my talk. So the rest of my talk is to explain that in two-dimensional CFTs, there are always conserved quantities, and whenever you have conserved quantities, going back to the conventional ETH, if you have only energy, then the expectation value of local operators in energy eigenstates is just energy dependent. But if you have other conserved quantities, you cannot avoid but saying that expectation values of local operators in energy eigenstates should also depend on those conserved quantities. Think about thermalization. If you start from some out of equilibrium state and then you thermalize, energy is conserved, and energy will define the eventual effective temperature to which you thermalize. But if you have additional conserved quantities, they are also conserved, and therefore if you start from the out of equilibrium state, the resulting equilibrium state will be dependent on the values of the conserved quantities, and they will be determining not only temperature, but also chemical potentials associated with all of those conserved quantities. And therefore, the statement of ETH, which was proposed quite early on by this group of people, is that this function, universal function, should be a function of all conserved quantities, and approximately giving you the expectation value of this local operator in the generalized Gibbs ensemble. That is the generalized version of ETH. By the way, my time is running short. I need to ask if I should try to finish on time or you will give me more time. What is better for you? I'm flexible.
Yeah, we are also flexible. We don't have a time that you can go on.
So I can go a little bit over time? Okay.
Yeah.
Okay. So this is a generalized version of ETH. There was quite a bit of numerical work trying to see how that works in integrable spin chains. I'll try to explain how things work in two-dimensional CFTs. In two-dimensional CFTs, energy eigenstates are primaries and descendants. You consider primaries and then you act by Virasoro generators to obtain an energy eigenstate. Then you have density of states of the primaries. That's the famous Cardy formula. Density of the states of descendants. That's you need to have Cardy formula for the primaries, and then combinatorics for the what is called partitions of integer partitions. That probably will be on the next slide, but that doesn't matter. What is important is that in addition to the Hamiltonian, which is an integral of the stress energy tensor, in any two-dimensional CFT, you have a whole tower of conserved quantities, which are integrals of higher powers of stress tensor and its derivatives. There is those charges, they are called quantum KdV charges. KdV stands for Kerdivec de Vries, a person who the history has it witnessed a soliton. I do not know to what extent this is a true story, but the story has it that the person saw the soliton propagating in a river stream, and this is related to Kardevec-de Vries equation. You probably heard of that. That's a classical integrable. KdV is a classically integrable system. This is a quantum generalization of this classical integrable system. It has infinite tower of quantum operators which are commuting with each other. They're indexed by odd numbers, Q1, Q3, Q5, and so on and so forth. Q1 and Q3 are written here. Q5 includes T cube and derivatives of T. There are only two guys, Q1 and Q3, which has no derivatives of T. All other guys have derivatives of T in their definitions. The expression of this Q guys in terms of Virasoro generators are very complicated. Of course, Q1 is L0 minus C divided by 24, but all other Qs are very complicated. And then what is important is that they're mutually commuting, and therefore you can define an eigenbasis called the integrable eigenbasis of states like this, but in fact, linear combinations of states like this, which diagonalize all of these Qs simultaneously. And then 3 years ago, already 3 years ago, we published a paper writing down explicitly spectrum of these operators in the limit of very large central charge. Okay, we will be working for now in the limit of large central charge, in the limit of, well, it's not necessary, but it's convenient. This slide is for any central charge, doesn't have to be large. You can look at the density of states of your full density of eigenstates, including descendants. It's produced by the density of primaries and the combinatorial formula, which is, I think, called Hardy-Ramanujan formula. This is the asymptotic behavior in the number of partitions of integer. The Hamiltonian is very degenerate. Let me say that. That's something which people know, but again, do not fully appreciate, that the Hamiltonian of two-dimensional CFTs are very badly degenerate. Energy of a state is equal to the energy of a primary plus the descendant level. But if n is a large number, there are many, many, many descendants with the same energy. How many? Approximately, I'm sorry. How many? Approximately that many. Exponentially many descendants with the same energy. And therefore, if you want to discuss thermalization in two-dimensional CFTs, and people these days discuss thermalization in two-dimensional CFTs all the time, you need to be very careful because the Hamiltonian is very degenerate. You can easily have states which will not thermalize at all because they will oscillate forever. You will have degeneracy between, you will have degeneracy, the energy spectrum here is equally distant because of this integer guy, and you can easily have an initial state which will oscillate because of this integer behavior with a certain periodicity and will never thermalize to equilibrium. That's just the result of the Hamiltonian being very, very degenerate. And since you have no thermalization, that actually is another sign of the fact that there is no eigenstate thermalization in case of two-dimensional CFT. So if you want to discuss CTH in two-dimensional CFTs, as people do these days, you need to be careful. You can discuss statistics of OPE coefficients, and that's what people usually think when they talk about ETH. But if you want to talk about thermality of eigenstates, that's a much more nuanced statement. Now, let me go back to the two-dimensional CFTs and try to calculate a typical representative, a typical state in the microcanonical ensemble. And if you do a very simple sort of saddle point approximation calculation, you will see that the typical state in the microcanonical ensemble will have primary given by this formula, and the descendant of it will be a descendant of this level and of this primary. Beta is an effective temperature. If L goes to infinity, it means that you are talking about a descendant of a very, very high level. So a typical state in the microcanonical window is not a primary state. It's a descendant state. This is known, but again, this is not very well appreciated. So primary states are not typical, and therefore local conserved quantities associated with the microcanonical ensemble are not the same as the local conserved quantities associated with the primary state. And this is a resolution of the puzzle related to the primary states not matching with the canonical or microcanonical ensemble. The resolution is very simple, and we understood this resolution already back in 2018. At least at the level of the principle, we understood how things are supposed to work. You're not supposed to compare primary state with a microcanonical ensemble, because microcanonical ensemble and primary eigenstates, they're supposed to be matching two different generalized Gibbs ensembles with two different values of this chemical potentials mu. Why is that? Because primary state and microcanonical ensemble have different values of these Qs. Okay? This is a conceptually important point to appreciate. You have an integrable system. You have, besides energy, many other conserved quantities. You should be comparing eigenstates with the eigenstates only if they have the same values of Q or similar values of Q. In the conventional case, you would compare different eigenstates with the similar values of energy. Now you need to be comparing different states or different ensembles only if they have similar values of Q. If they have different values of Q, it makes no sense to demand that corresponding states would have similar local quantities, local properties. They actually should not have similar local properties. That would be strange if they have similar local properties. In fact, you can show that they cannot have similar local properties because operators Q are local operators. And so far Qs are different, it actually means that they have different local properties. So if you think about it, there was no puzzle to begin with. Any puzzle, when you resolve it, you understand that there was no puzzle to begin with. So there was no puzzle to begin with. The puzzle was only because you were trying to do something which was wrong to begin with. You have integrable quantities. You didn't take them into account. That caused the problem. Once you take them into account, you understand that the rules of game are completely different. You should not compare primary eigenstate with a microcanonical ensemble. Okay? But now that we understood in 2018, that is written in this paper, what did we do recently? What we did recently, okay, this is another slide about ETH and two-dimensional CFT, but what we did recently is the following. We actually understand that there is a variety of generalized Gibbs ensembles depending on the coefficients mu. And you can play with those mu's, and you can take, for example, an ensemble which includes all of these mu's, and then you can turn all of them off except for the first one, which we will call beta because that's effective temperature. And if you turn all of them off, you will end up with a thermal ensemble or conventional Gibbs ensemble. Or you can try to tune these mu coefficients such that you will try to describe local physics of the primary state. And what we did recently in this 2024 paper, we actually considered different generalized Gibbs ensembles. We used results of different papers, a combination of different papers, 2022 paper, 2018 paper. That's a different paper from what I showed you before. That's a different paper where we calculated free energy of the generalized Gibbs ensemble. You can use this free energy to recalculate entropy, thermodynamic entropy, and you can use thermodynamic entropy as a density of states, and you can use density of states with a diagonal approximation to calculate the subsystem entropy. So you go through all of these technical steps, but finally what you have a formula for the subsystem entropy of a generalized Gibbs ensemble as a functions of mu's. And now you can play with mu's and you can try to go and try to describe different local physics. You can try to describe the conventional thermal ensemble, or you can try to describe primary eigenstate. And this is what we did. This is what we did. You actually have to consider the GG with only two chemical potentials. One can be considered as temperature, another is auxiliary one. And you have two regimes. There is a regime of a conventional canonical ensemble when you take mu3 equals 0. Then it's just you remove that, and that's a conventional canonical ensemble. Or you have another somewhat special regime where you keep mu1 divided by mu3 fixed and take mu1 to minus infinity. And in this regime, this ensemble will describe primary eigenstates. All of them, statistically, because all primary eigenstates have similar physics. They're similar to each other. They form their own universality class with their own values of Q's. And they're all described by this singular value of the generalized Gibbs ensemble. And then you can use this diagonal approximation with the explicit knowledge of the density of states, which is a function not only of energy density, but also density of conserved quantities Q3, Q5, and so on and so forth, to recalculate subsystem entropy. And this subsystem entropy matches precisely the result we obtained before. The simplest test that this is a correct result, you see no n dependence in this formula. This is a formula for any entropy. I forgot to put n and a here. This is a formula for any entropy. There is no n dependence here in this particular limit. So basically, the puzzle is resolved. We see that the GG ensemble interpolates between different regimes, and you produce correct formulas in all the different regimes. Okay, just maybe I don't want to. I know that we are all very tired. This is one of the very last slides. We consider different regimes, and the interesting thing is that there are transitions. When you try to do the calculation using the diagonal approximation, you need to do the integrals via saddle point. And there could be different dominant saddle points depending on the size of the system or the index of the Rayleigh entropy. And depending on that, you can have different explicit expressions for the subsystem entropy. And because we calculated things explicitly, but maybe I can just show you a plot. So this is more like a phase transition. This is not X, this should be called F. This is a fraction. And this is the subsystem entropy in the generalized Gibbs ensemble as a function of fraction. And blue line is a naive value, but because of this different saddles, you actually have the correct formula being blue, which goes into orange. So this is a behavior which is qualitatively similar to other phase transitions, which people observe for any entropy holographically. Sometimes, like let's say you have two regions, and depending on the geometry of two regions, you can have two different Rutakanagi surfaces connecting those two regions, and you have a phase transition between those two surfaces. This is a very similar phenomena, but for a one subsystem when the full system in the generalized Gibbs ensemble. And you can try to understand that holographically, and holographically, you literally have two holographic solutions for Rutakanagi surfaces, and both of them contributing, but one saddle is dominant, and when F crosses this critical value, then another saddle becomes dominant, and you're sitting on another branch. Okay, I think we are going into some very, very technical details. I also wanted to mention that diagonal approximation have very clear counterpart in holography and has been studied recently in holography. Maybe that's all. I should maybe conclude. What did I talk about today? in a nutshell, I was trying to explain that there is a very powerful approximation to calculate subsystem entropy in different physical systems. In conformal field theories, it's particularly good because it gives you a lot of universality. With that approach, we calculated we calculated entropy for many different states. We got a lot of explicit results for the system being in the generalized ensemble characterized by KdV charges. I didn't mention that in addition to generalized Gibbs ensemble, you can also consider generalized microcanonical ensemble. When you say that you have states with the values of Q's in a certain window, and you can also calculate entropies for those states as well, and we did that in a paper. So you got a lot of new explicit results. It's very clear that this method has application to other settings as well. One very natural area is to try to use it to calculate subsystem entropy for spin chains, like XXZ spin chain, which has a lot of conserved quantities. I do not think that has been done, and I think it's a very promising direction. But of course, there are a lot of overlap with other works about CFTs, OP ensembles, vacuum entropy in two-dimensional CFTs, and other universality results. I think there is a way to connect our approach to those methods as well. I think that would be all for today. Thank you.
Thank you for this great presentation. We can take questions right now. If no one has a question, I can ask one. Okay, go ahead. No, you.
Yes, thank you for the talk. It was very nice. So I have one question in the case of CFTs. So in regular systems, right, ETH is only somehow talking about linear observables, and it's kind of silent about nonlinear observables. And people discuss various generalizations, and this is important for like Renyi's because you have multiple copies of the state. In the case of CFTs, however, like OPs let you decompose higher order operators into lower order ones. So does this like say anything about the generalized ETH statements for the CFT case?
I'm not sure what you meant by non-linear observables. You mean something like Renyi's, right?
Or something, you know, where you have like 4 local operators in a correlation function. That would give you...
That is a linear observable, right? That's just an operator. It's a composite operator. If you have 4-point function, that's still a composite operator in your CFT. I think there is a conceptual difference between Renyi and 4-point correlation function. 4-point correlation function in the end of the story is an expectation value of a composite operator in a state raw. It's like trace, raw, and then whatever operator you want. But in terms of raw, it's a linear quantity. So that's a conventional quantum mechanics. Renyi entropy is slightly different because Renyi entropy is non-linearly dependent on raw itself. Or von Neumann. Von Neumann is non-linearly dependent on raw itself. That's why entropy is such an interesting quantity, because it's nonlinear in the density matrix, right? Or quantum mechanical state psi. Now, we calculated Renyi entropy in this talk today. There was no problem with that. You calculate, you use this diagonal approximation to calculate reduced density matrix, then you take it to an appropriate power. That is exactly how you do the calculation. So there is no issue with local linearity and non-linearity. The statement of subsystem ETH is that subsystem state of a global energy eigenstate has universal form. And this universal form is precise up to exponential corrections. So whatever you do with the subsystem density matrix, you take it to a power, you take the logarithm of it. So far, you're not sensitive to exponentially small corrections. You should be fine, right? What is the statement of generalized ETH? There might be a statement of generalized subsystem ETH that the reduced density matrix is universal if you fix all quantities Q, right? There might be a statement like that. But unfortunately, in case of a CFT, I have preliminary evidence that this universality will not be satisfied with the exponential precision. That's the issue. It's not the formulation of ETH, it's more like how it works in two-dimensional CFTs. I have actually a slide which I glossed over because I felt I didn't have time to describe it. This is a work we did in 2019. We were trying to see if generalized ETH actually works in two-dimensional CFTs. So for that, we considered expectation value of local operators and energy eigenstates. And these operators, we considered these are descendants of the identity. So in other words, these are operators which are made out of stress tensor and its derivatives. There is an explanation why we don't have to worry about primaries. The idea is that if you have chaotic CFT, you expect that all primaries will have zero expectation value because of the behavior of the OP coefficients. But descendants of identity, they are fixed by integrability structure. They're not related to OP coefficients because they are related to the identity operator. Identity operator always has non-zero expectation value. Expectation value of identity is always identity, right? So it's just identity as a matrix. So basically, you take a descendant of identity and you calculate expectation value in any energy eigenstate. We were trying to see if you can match that to some smooth function of charges Q associated with this energy E. And at the first non-trivial leading order in 1 over C, we were able to do that. There are functions A of Q, very explicit functions A of Q, which are actually polynomials. Every single operator A has its own polynomial of Q. We found those polynomials for a handful of operators, and everything works beautifully. And you can ask, what are the corrections here? Usually you have exponentially small corrections. Let me gloss very quickly to the beginning of the talk. The width of this curve is exponentially small, right? You cannot see how small it is. You see that it is small, but it is actually exponentially small. If you increase the size of the system by 1 spin, then roughly the width of this curve will decrease twice, roughly. Every single time you double the number of states in your Hilbert space, your curve will roughly become twice smaller. Here, there are no corrections to this formula altogether. It actually means that ETH is satisfied precisely, and there is no exponential fluctuations around the ETH. That's the amazing result, which I do not have any good explanation for, except that we calculated it. But more recently, we calculated next 1 over C squared correction, and we expected that maybe this correction will be exponentially small, but it happened to be only polynomially small. That is a big surprise to me. I do not understand what is going on. I'm very confused by this result. This result is unpublished. Maybe it should be written, but I do not understand the physics of it. That's maybe the reason why we didn't write the paper, because instead of the conventional exponential suppression associated with ETH, we saw that in the next 1 over C order, the suppression is polynomial in the system size. If the suppression is polynomial in the system size, it means that you likely have subsystem version of generalized ETH. And let me put that formula in front of you. This is the conventional version of subsystem ETH. You will have a generalized version such that 2 eigenstates should be compared only if their Qs are satisfied. But instead of exponential suppression in terms of the entropy, you have something like 1 over S to certain power. Or
But somehow
1 over...
this,
Yes.
But this is super weird, right? I mean, you have like some heavy tail distribution with like thermodynamically large fluctuations, effectively, right? Because that's fascinating.
I agree that this is very weird. I told you
Yeah.
the full story, and the full
Yeah.
story is even more weird because at Leiden 1/c order, instead of exponential suppression, you have 0. And the second order, instead of exponential suppression, you have polynomial suppression.
Yeah, this
So
is super weird.
at first order, you have too much precision. At second order, you have not enough precision. I do not know if precision is the right word here. I don't understand the physics of it. Let's put it like that. I'm rather confident with our calculation, but I don't understand the physics of it. That said, I think you will have a version of subsystem ETH, but since you have only polynomial suppression, it might be that if you start doing weird things with your density metrics, taking it to some power, stuff like that, those polynomial suppressed terms could matter. I didn't think much if they would matter for any entropy or when they would matter for any entropy, but it's very clear that polynomial suppression is a weak form of suppression and it could matter.
Right, this is very interesting. Thank you. Yeah.
Okay. Yeah, so sorry, this is of course a technical detour into some unpublished work, but to address your question, I had to tell you this technicalities. And
very much appreciate it. Yeah, thank you.
Yeah, I to some extent know the literature about spin chains. I don't think people understand very well for the spin chains if the corresponding terms in the generalized ETH, if they should be suppressed exponentially or polynomially. People try to study that numerically, and that's very difficult because when you have generalized ETH, your statistics is very small because you need to resolve your eigenstates with respect to Qs, all of them. So your statistics is numerically very small. And then there is no good analytic way to understand whether suppression should be exponential or polynomial. That is at least the status of 2022 when I talked to the experts last time. So anyway, well, maybe we should end on an optimistic note. How every single time I hear a talk by Nimar Kanihamed, he says this is a wonderful opportunity for young people because there are so many unsolved questions. So certainly there is some interesting physics to understand. And I will be happy to admit I don't understand this physics right now.
Thanks, that's exciting. Thank you.
Hey, are there any other questions? Maybe I can ask the first thing that comes to my mind. Can we make any progress on higher dimensional CFTs? Because I think there are no KdV charges and integrability. So, and should
it depends what you want to do. In some way, it was done long ago, right? And I'm not talking about our paper, although our paper recalculated all the entropies which are in front of you right now. But I think some of these results, if not of them, were known because of holography. Of course, you can say it was derived in only holographically. Now we have a more general derivation, which suggests that much larger class of theories will behave this way. But basically, for high-dimensional CFTs, I think these are the answers. I do not think there is a version of GG, generalized Gibbs ensemble, for high-dimensional CFTs. So it's not clear what exactly you would like to do beyond this.
I was asking with this procedure, can we recover? I mean,
you mean the diagonal approximation?
Yeah.
Well, these results are obtained using the diagonal approximation. You can look in our paper. It's a very straightforward calculation.
Okay.
If you're interested in this method and you want to know what can be done, I have a project for you. What I didn't think much about it, but I think one can try to do a two-region calculation, either in 2 dimensions or in high dimensions, just using semi-classical diagonal approximation. One has to calculate integrals using saddle point. And I have an expectation that when you try to do that, there will be different regimes dominated by different saddles, and that will have a counterpart in a Rüther-Kayanagi surface having two different saddles holographically. But you don't need to work with the holographic CFTs. You simply work with the chaotic CFT, if you wish. And the calculation, I think, can be done in any dimension. It will be interesting to see if there are saddles different phase transitions in higher dimensions, and what are the conditions, what are the geometry of the subsystems when this phase transition occurs. That, I think, is an open question, and I don't think it was discussed in the literature.
Okay, thanks.
Maybe two regions or more complicated geometry of the regions is the way to go. Let's put it like that.
Okay, if there are no other questions, we can stop to.
Can I ask a question?
Yeah, sure.
So first of all, thanks for the nice talk. I wanted to ask, like, at some point you had Cardi formula and you had some torus on the CFT. So when we have a CFT on torus, we have modularity and SL2Z action. How does that modularity manifest itself in ATH? Like, what kind of constraints we can get using that SL2Z action?
Right. Well, this is a good question, but so let me tell you one thing. Cardi formula. Where is the Cardi formula? Somewhere here. This is the Cardi formula. Of course, Cardi formula, he derived his formula using modular properties. We understand Cardi formula holographically as an entropy, Bekenstein-Hawking entropy of a BTZ black hole. But in fact, we can understand Cardi formula in a very, very simplistic way from here. And we write that explicitly in our paper, just one line comment, but you can read there and you will immediately understand what we mean. In 1 + 1 dimensional system, D is 1. In this case, it's a 2-dimensional CFT. Cardi formula is telling you that entropy is proportional to the length and then multiplied by the temperature to the power 1 because of the dimensionality, because entropy is a dimensionless quantity. The only non-trivial content of the Cardi formula, in the sense of so far you're interested in the extensive part of the entropy, is that Cardi formula tells you that this kappa is related to the central charge. That is what dimensional analysis cannot tell you, and Cardi analysis, of course, tells you. But if you don't care about what the meaning of C is, what kind of quantity it is, if you are happy with any number in this formula, in the Cardi formula, then there is no mystery behind the Cardi formula. It's just the statement that the entropy is extensive. Okay? Okay, so that is, again, a very simple thing, not widely appreciated thing. People know historically how Cardi derived his formula from modular invariance, but it actually is a statement that entropy is extensive. Now, speaking about ETH and modular properties, I don't want to dismiss the idea that modularity has anything to do with modular with ETH, but I would rather say that the relation is not a straightforward one. There is a series of nice, interesting papers starting in 2023 where people try to merge modularity with the statement that spectrum of primaries should obey random matrix theory statistics, which is a sign of chaoticity. These are very nice formulas, nice papers which develop a mathematical formalism how to combine modularity with a statement that your eigenstates of Hamiltonian obey RMT statistics. ETH, in some very simplified way, is a statement that eigenstates behave like eigenstates of a random matrix. That's not literally correct. you have a lot of additional constraints, but at least at the very, very first approximation, you can think of ETH as the statement that individual energy eigenstates are eigenvectors over random matrix. So one can think that later, sometimes later, people will extend this work RMT plus modularity to eigenvectors. That would be what you want. That would be the ideas of modularity constraining ETH. Okay. I should probably mention that in 2018, there were a series of works and also later on where people use modularity to constrain average value of OPE coefficients. That is very well known. And now people, in 2022, people match those average values of OPEs to holographic picture where they saw that these average values of OPEs on a CFT side produce classical geometries or action of the Hilbert-Einstein action on classical geometries on the bulk side. So this is basically modularity dictating certain constraints on the statistics of OPE coefficients. That is certainly related to ETH. But that is not related to thermality of individual eigenstates the way I was talking about them today. That is more the part of the ETH which talks about matrix elements or OPE coefficients.
I see. So there are ideas, but nothing is very concrete established about modularity in that context.
Well, in the context of OPE coefficients, it's very concrete, and modularity was used very heavily. That
but
is
in ATH.
It depends what you call ETH. Many people, including authors of that paper, of those papers, call that ETH, and that's fine. That's fine. Although I prefer to call it OPETH to distinguish, but that's really not the statement of thermality of individual energy eigenstates.
Okay.
Okay, it's a different statement. For them, the statement of thermality of individual energy eigenstates is a statement that is this one. Is this statement that heavy light OPE coefficient goes to 0 when the dimension of the heavy operator goes to infinity. Sorry, that is a type. It should be infinity. That statement, they basically take for granted. They postulate that this is true and then try to understand what modularity says on other about other OPE coefficients. Okay.
I actually have another question. So you said that we take delta to be a large number. Can we use the ideas of large charge expansions to establish anything about this? Like maybe we constrain to the large delta sector in the CFT and try to understand this statement?
I had an impression that large charge expansion uses the ideas of ETH to do something about large charge. Maybe there is a way to borrow back what they understood there, but I'm not sure.
But it may be circular. That's what you're saying, right?
I had an impression that we are already using the same set of ideas, that there is but I could be wrong about that. I don't follow this area very closely, so there might be some developments which are worth looking into.
I see. Okay. Thanks.
Okay, we can actually stop recording, and maybe if there are people want to ask questions off recording, they can ask